Every app on your phone is a prisoner, completely isolated in its own sandbox. So how does it ever talk to the rest of the system? Here's what's actually happening. Android enforces what the highlighted text calls a strict separation between kernel space and user space. This isn't just a suggestion, it's a hard boundary enforced by the CPU itself to keep the entire system stable and secure. A bug in one app shouldn't be able to bring down your phone. Now, let's look at how the processor actually builds this wall. So why can't your app just decide to turn on the microphone whenever it wants? Because the CPU itself has different modes of operation. Notice the highlighted text operate in different privilege modes. Think of this like a building with a regular floor and a high security vault. Your app runs on the regular floor with a low privilege keycard, while the kernel operates inside the vault with a master key. The trick that took me years to learn is that this isn't a software concept, it's baked directly into the ARM processor's silicon. Let's look inside that high security vault first. Inside this vault is kernel space, the absolute heart of the operating system. As you can see highlighted, code running here has unrestricted access to the underlying hardware. This is where the core Linux kernel lives, managing memory, scheduling processes, and talking directly to the chips. Most people trip over this because they don't realize the danger. If code here crashes, the entire system panics and reboots. That's a kernel panic, and it's infinitely more serious than a simple app crash. This is why we protect it so fiercely with a less privileged space. So if the kernel is the high security vault, where does your code and almost everything else in Android live? It lives in user space. Look at the highlighted text here. All applications and the majority of the Android framework run here. This is the low privilege area. Code here is strictly limited. It can't touch hardware, it can't read another app's memory, and if it crashes, Android's activity manager just cleans it up and moves on. The phone stays on. Let's see just how much of the system actually runs in this safer space.
Most people are shocked when they learn what actually runs in user space. It's not just third-party apps. As the highlighted text shows, it's also the launcher, settings, system UI, even the mighty system server process, which manages almost the entire framework, is a user space process. Since Project Treble, even the hardware abstraction layers, or HALs, were moved into user space. This design ensures that a bug in the Wi-Fi HAL, for example, can't compromise the entire kernel. But if all that runs here, what is the kernel actually doing? The kernel handles the absolute non-negotiable core functions of the entire system. Look at the responsibilities listed here, starting with memory management. The kernel is the ultimate gatekeeper. It decides which app gets to use the CPU next using the scheduler. It contains the low-level device drivers that send the actual electrical signals. And critically, it runs SE Linux to enforce security policy. It's the trusted foundation. So we have this perfect wall, but how does anything get across it? If your app is trapped in its user space sandbox, how does it ever read a file or open the camera? It can't do it directly. It has to ask the kernel for permission. As the highlighted text explains, this request is known as a system call or syscall. This is the only legal way to cross the boundary. Your app packages up a request, hands it to the kernel, and waits for an answer. Think of it as filling out a form and passing it to a government official through a tiny slot in a plexiglass wall. Now, let's trace exactly what happens during that transaction. Here's what actually happens under the hood during a syscall. As the highlighted text describes, the CPU pauses the app, switches from low privilege user mode to high privilege kernel mode. This is called a context switch. The kernel then takes over, validates the request. Does this app have the right permissions? Does SE Linux policy allow it? And then performs the action on the hardware. Finally, it packages the result, switches the CPU back to user mode, and wakes your app up. You can actually watch this happening in real time.
You don't have to imagine this. You can see it for yourself. The highlighted command here shows how to use a standard Linux tool called strace. If you run this exact command, adb shell strace -p
$PID off surface flinger, you will get a live fire hose of every single system call the screen compositor is making to the kernel right now. You'll see it asking for memory, waiting on fences, and talking to the graphics driver. This visibility is why understanding the boundary is so critical for an AOSP developer. So why do we obsess over this boundary as platform engineers? The first reason is security. As this highlighted line explains, vulnerabilities in kernel space can lead to a full device compromise. A bug in a user space app, like a media parser, is bad. It might let someone read your data. But a bug in a kernel driver is a catastrophe. It allows for privilege escalation, which is how most device rooting exploits work. It's the keys to the entire kingdom. But security isn't the only reason. This boundary is also a major factor in performance. Notice the highlighted text. Crossing the boundary via a syscall is computationally expensive. That context switch I mentioned isn't free. It takes time and CPU cycles to save the state of your app, enter the kernel, and then restore it. This is why high-performance code like audio processing or graphics rendering is carefully engineered to batch work and make the fewest number of syscalls possible to avoid jank. Finally, this boundary completely changes how you debug a crash. When things go wrong, the location of the crash determines everything. A user space process gives you a nice crash log called a tombstone. But as the text here points out, if the kernel crashes, you lose ADB access. You're completely blind. The only way to debug a kernel panic is with low-level hardware tools like a serial console or by analyzing a special memory dump from a feature called pstore. It's a completely different and much harder world of debugging, which is why we work so hard to keep bugs out of kernel space.
Enjoyed the video? Hit like and subscribe for your regular dose of AOSP customization. Thanks for watching. See you in the next one.